All right. Good morning, everyone. Thank you for coming bright and early today. So we're here to talk about our work on standardizing requirements for accelerators, especially in the context of hyperscalers and GPUs. My name is Sujoy Sen from Google, and I'm joined by my colleagues from AMD, Meta, Microsoft, and Nvidia, who will speak through the rest of the presentation and introduce themselves. And what we'll do is we'll walk through the why and what of this effort, and then go through the three specific areas that we've chosen to attack, as part of this effort. So I'm going to talk a little bit about the why and the what. So about a couple of years ago, Google, Microsoft, and Nvidia got together, and then were later joined by AMD and Meta to think about how to standardize common, non-differentiating, but yet very critical requirements to ingest, operate, and manage GPU products at scale and with some velocity in our hyperscaler data centers. And it turned out that there were a lot of common themes and elements and pain points that we wanted to address. And there were so many, we had to sort of whittle it down to three areas. Whittled it down to three areas. The first was management interfaces, which sort of provides the bedrock or the foundation for standardizing anything else that we want to do. Much like the previous, the earlier talk by on Redfish sort of profiles, OCP profiles, this is looking at very GPU-specific or accelerator-specific interfaces. And then we chose two vertical domains that are particularly important when it comes to operational and reliability aspects, especially at the scales that we tend to operate these products in. So one of them is firmware update. And often, something that we do very often and is very critical to keep these systems alive and well. And then, of course, RAS, which is a wide topic by itself, but extremely important to keep our systems reliable. And the approach we took was, so we worked on specifications and, excuse me, these are really requirement specifications as well as some level of interface definitions as well. And for these three areas. And then a somewhat unique thing we did is we developed a compliance tool that would check against products against compliance against these specifications. And there's a talk on that later today at this very room at 4 o'clock. Which I think is going to be even more exciting than this talk. So please be sure to attend that. And just from a progress standpoint, we published a 0.5 version of these three specs last year around this time. And I'm happy to say that we have reached the 1.0 milestone. And with that, let's get into each of these three topics. And I'll hand it over to Krishna, who will talk about management interfaces.
Thank you, Sujoy. Hi, everyone. My name is Krishna Sugumaran. I'm from AMD. I'm going to talk about how we are trying to standardize GPU management interfaces. Right? Let's dive in. There are two main areas of focus here. Right? The first use case is a discrete accelerator device where we have a GPU in a PCIe form factor card. Right? And the out-of-band functionalities in this use case is implemented within MC or the MC could be within the GPU on chip, or it could be off chip in a microcontroller, right? But the role of that MC is to implement all the out-of-band functionalities that include MCTP, PLDM type 0, 2, and 5. over the I2C or I3C or USB medium, right? But the essence of that management controller is to manage the GPU and all the onboard components like VRs and other sensors, right? The sensor telemetry, the firmware updates, the sensor monitoring, reporting, and the security side of things are managed by that MC. And in this use case, we are trying to standardize the interface between the hyperscaler BMC and that MC. And again, as you see, this is all using the DMTF protocols, right? MCTP and PLDM and SPDM. We are not deviating in any way from any of these standard protocols, just that we are coming up with a profile or a minimum subset of all these functionalities that are needed to enable a PCIe form factor card like this. That meets both the hyperscaler and vendor requirements. That's the use case number one. And in the second use case, this area of focus is the UBB, Accelerator UBB. And in this case, we have a management controller, onboard UBB, that's called Accelerator Management Controller, AMC in short. That is responsible for managing all the GPUs in the OEM form factor within the UBB and all the onboard peripheral components like VRs, retimers, FPGAs, right? And the role of this AMC is to collect all the telemetry from all the downstream devices and pass it on to the hyperscaler BMC. That's the single point of contact between the hyperscaler BMC and this UBB, right? But here, again, the goal is to standardize the interface between the interface requirements between the hyperscaler BMC and the AMC, and it is out of the scope of this work stream to standardize anything downstream between the AMC and downstream devices, or anything upstream between the hyperscaler BMC and the data center management software, right? So there is a specific slide to talk more about the Redfish standardization, but prior to that, let's see the progress we have made since the last time we met here, right? We've added AMD and Meta as new workstream members, and we have published, as Sujoy was saying, we have published a 0.9 version of this specification to the OCP portal. That includes some minor clarifications around IPMI through data, MCTP OEM VDMs, and a PLDM sensor and effectors. And we've also added some clarifications around SPDM, right? So we've added the inputs and feedback from new members like AMD and Meta. And finally, but not the least, right? We have spent last 6 months or even more standardizing the Redfish interoperability profile, right? We have specifically for GPUs UBB. Right, we have added 0.91. We've released 0.91 specification to the GitHub, OCP GitHub, back in summer. But in the last couple of weeks, we also managed to release 1.0 specification to the GitHub, right? And let's talk more about the UBB's Redfish interoperability profile, RIP in short, right? So what is RIP? RIP standardizes the Redfish requirements between hyperscaler BMC and UBB's accelerator management controller, right? So as we all know, the Redfish is vast, right? And there are hundreds of schemas and thousands of properties, and it may not be viable to implement all this, and it may not be even necessary to implement all this in a single product, right? So to mitigate this, we have painstakingly and meticulously compiled a list of all the all the properties and schemas and functionalities needed within this Redfish that meets the requirements of hyperscaler BMC and the vendors, right? So that's, as you see the highlighted Redfish resources, it spans across the entire Redfish tree, right? So yeah, so this profile is basically a subset of all the Redfish functionalities needed for this product. And I'm happy to say that currently shipping products from both AMD and Nvidia are 100% RIP 1.0 compliant, and there are the subsequent speakers are going to talk about some of the use cases like firmware update and RAS in more detail. With that, I'll hand it over to Vishal. Thank you.
Thanks, Krishna. Welcome, everybody. Good morning. Thanks. I'm going to disappoint you. I'm not going to be able to go into any details whatsoever in 7 minutes I have. So let's spend 7 minutes understanding the mission, what we did last year, and what we achieved so far. So we started off with a mission of standardizing GPU firmware update requirements to make them simple, fast, and reliable. One thing I'll be happy if you walk away from this talk is to walk away with the phrases fast, simple, and reliable. That's the theme for firmware update standardization that we are aiming for. right? Before we, you know, so I just wanted to put GPU in perspective because it's not just the discrete GPU that we are talking about. We're talking about two flavors. I think Krishna also touched upon it briefly, but I wanted to give a zoom in view of it. GPU could be a PCI card with one or more GPUs on it, or it could be a UBB baseboard with secondary components around it. And when we are talking about standardization of GPUs, we are talking about standardization of firmware update for both form factors, right? There are dime a dozen protocols supported by different components from different vendors. How do we unify the update mechanism, right? What should be the packaging format for all of these components that a vendor ships the package to a hyperscaler or a OEM or ODM to, right? What would be the security posture? What components are covered or not covered? So we nailed all of those requirements in 0.5 spec last year, and we are happy to share that currently with 0.5 spec, you have a simple way, 3-click, I should not say click, 3 API orchestration method where you push the firmware bundle. Bundle is a composition of multiple firmware images onto AMC or UBB baseboard, apply the bundle and activate the bundle. With that mechanism, with these 3 APIs, you can orchestrate firmware update of UBB in less than 10 minutes, and we have tested that at scale. And my friends here and in the crowd can attest to that as well. So what happened between last year and now, and please keep me honest with time here, I might get carried away here. So although we achieved the simplicity and the speed, as we saw in keynote yesterday, the scales at which clusters are are evolving is fast. So we wanted the speed. We realized that the speed is not fast enough. So we wanted to optimize, opportunistically optimize the speed at which firmware update happens. So we came up with a split staging approach per se, and we can get into details after the talk. I can walk you through the the guts of it. The idea is to be able to securely stage a firmware close to SPI-ROM so that it can be activated later point in the time when you take a downtime for the system. So again, firmware update process includes copying the payload onto EEPROM, arming it, and then activating it. So what we have done is we have disaggregated the act of copying the payload onto EEPROM and activating it, so that you have a cluster of 10,000 nodes. You opportunistically land all the images on EEPROM. You take downtime and activate it all at once, or you can stage activation as well. The other thing we wanted to hash out was the disaggregation of rollback protection or security version enforcement from firmware update process, right? In last year's work, it was tightly coupled to the hip. Now we have put in requirements so that, based on user persona, you can either activate it when or you can apply minimum security version when firmware is updated autonomously, or you can create a workflow which arms minimum SVN on demand. So that gives people a chance to vet out the new firmware that is rolling out before you lock yourself out of the previous known good firmware versions. Right? Again, I think I might be out of time here. We buttoned up aspects of firmware packaging, end user error handling scenarios, which is very vital in hyperscaler use case, or for everybody that, for that matter. When a firmware update fails, we got to know why it failed. Did it have a communication failure? Did it have a security failure? Do you have a hardware failure, whatnot? So getting that information back instead of having a spinning wheel is vital. And we nailed down those exact message items in the spec as well. So I do encourage you to go and check out 1.0 spec and remember 3 words: fast, simple, and reliable. Thank you.
Hi, I'm Rama. I work at Microsoft as a RAS team lead. Hello. Hi. I'll be presenting with Anil Agrawal from Meta. As Vishal said, like we have just 6 minutes for the talk. We'll just highlight few of the high-level contributions we did as part of 1.0 OCP GPU RAS accelerator requirement spec. Before we just discuss the details of the spec contribution, want to highlight few critical goals for this, the RAS 1.0 requirements document. First one is like many people are already familiar with general purpose workloads, right? You have multiple VMs per node. When error happens, all this with fatal errors, you see the workload disturbed, impacted with that fatal error. Whereas in the synchronous data parallel training workloads, the scale of systems at a data center level, you're dealing with supercomputer kind of scale to run one workload. Few of the key pain points we have is at the scale of this parallel workload spanning across the data center AA supercomputer, even one system performance issue due to link health or error storms can impact performance of full AA supercomputer. Think through that, how much big impact errors can have on the training workload performance. Second key point is with fatal errors, like one GPU or system level reboot can increase the training workload times, job completion times, to few days to weeks, okay? Think through scenario like if error happens every 4 hours at that scale, it is impacting the checkpoint restoration, it can add, okay? Those are the critical availability, reliability metrics. And third thing we focused on standardization was interfaces to in-band management agents and cloud scale agents to look at the telemetry, error telemetry. How do we do predictive maintenance of the systems? How do we do debug and diagnostic services at the scale of? For these 3 pain points, we focused on the UBB and the PCIe system designs. As you see in the UBB designs, we have GPUs with a lot of memory, I/O, interconnect, and switches. We specified the system level, memory level requirements to meet some of the pain points I discussed. And if you see from last global summit, we contributed 2 versions of the spec, 0.9 version mostly focused on the critical issue RCA SLAs. At this scale, at the complexity of the issues, how do we debug these issues at scale faster? The focus on how do we collect system level, component level crash dumps, and what are the requirements, standardized requirements for collecting the crash dumps? How do we analyze that? Collection is just a half of the work, and how do we analyze and do the repair actions? And with 1.0 version, we got a lot of feedback, and we extended the RAS requirements And also the way we structure the RAS requirements about, like we focus on the metrics. What are the RAS requirements? You know about traditional metrics like fit rates, mean time between failures. We extended that metrics to like AA supercomputer, like job interruption rates, mean time to restore the jobs, okay? Based on that requirements, we proposed some of the targets. The targets can vary from hyperscaler to hyperscaler. And the 1.0 spec delves into more system level requirements like error containment. How do we handle error storms? How do we deal with uncorrectable errors? Okay, we're not going into details because of the time. And it also talks about memory level requirements. And one of the theme we focused is there is a OCP hardware fault management work stream which supports multiple RAS initiatives. We are in comply with like overall hardware fault management requirements, like and even though we specified the detailed requirements, the RAS is a lot of innovation can be done by the vendors, right? Silicon vendors. We have given flexibility to like vendors to innovate further. We are like standardizing some of the critical requirements. Okay, the main thing is like is a lot of hard work over last 18 months. We're happy to announce that we're contributing that 1.0, and there are 10 plus contributors. Some of them are here. Thank you for. Okay, Anil will be discussing on what we'll be doing next.
Thank you, Rama. So I'm the last one. You'll deal with me for a few more minutes. So it was a long journey. We started developing these requirements almost, 1.5 years back. And we are all happy to say that, yeah, we have 1.0 now. And we are just 5 people over here, but there are many, many people who worked on this. So thanks to everyone who has contributed to achieving 1.0 version of the spec. Now, you may wonder, once we have released 1.0, what is there? We are done, right? 1.0 is done, work is done, let's go and move on to something else. The reality is that we are not done yet. We've got a lot more work to be done. And obviously, RAS is not something very simple that we write something on the paper and done, because it touches so many different areas that we need to make sure that we cover all those areas and also put the requirements with the adjacent specifications as well as the works going on. So these are the 5 areas that we are going to work beyond 1.0, listed over here. Let me just give you a little more background rather than just reading those bullets. So how many of you have heard about, actually Rama already mentioned that, so he already clarified that, but how many of you heard about hardware fault management sub-project? Good, at least some of them. So this is not the first time we are developing a requirement, RAS requirement in the GPU world. Hardware fault management requirement and specifications have been developed, we have been working on it for many, many years now. And this GPU RAS requirement actually started in parallel. Although we were all collaborating, but still a lot of work needed to realign with the hardware fault management sub-project, which is already going on, and there is already 1.0 requirement released, and now we are working on 1.5. And within that umbrella, there is a RAS API. So how many of you have heard about RAS API? So believe it or not, we are developing APIs for RAS. Never heard about that, right? So yeah, so we want to make sure that the GPU or accelerator RAS requirements and the specifications are aligned with the RAS API specification that we are putting together. So that's the one thing we want to do. Now, error injection and crash dump. Crash dump, there was discussion just before this talk, right? So error injection is area that we did touch in 1.0. We have some very high-level requirements, but there's a lot more work need to be done. We are not there yet. How do we do error injection out of band? Can we do it even? That's all discussion going on. Can we do in-band with out-band notification, something like that, right? So we need to work on that. Crash dump, we have also added in 1.0, crash dump, concept, but there are a lot of details. So we're going to work on that. Confident computing, all this trusted environment, there are some overlap with the trusted environment. You may be wondering how, why? Well, when there's fault happens, uncorrected error, poison, it goes all the way to the application. It can actually, right? So the poison data is a data path. Now, how do we ensure that when one trusted compute is getting some data with a poison bit set, doesn't affect other workload, trusted workload, right? So we need to make sure that we align with that. So some of the work need to be done there. Now, next thing is defect screening. So a lot of manufacturing tests already happens. We screen the parts, but still there are some latent faults that can happen in the data center. So how do we align with those requirements in the GPU world, in GPU RAS requirements? And finally, I think Krishna mentioned, or Sujoy, that there is a compliance tool that is being developed to make sure that all the requirements, specifications we are putting together can be tested autonomously. So this compliance tool, we started working on this one also, but we are not done yet. So we are going to work on that also. So these are the 5 areas that we're going to work on to get to the next version. We don't know what that is going to be, 1.5 or whatever, but we're going to work on that. So any one of you who's interested, getting excited about in this area, please reach out to us. There is a link here, or any one of us, and we are looking for any help from the community to support us and bring some thought process, learning from the past, to make these requirements and specifications as robust and useful for all of us. Thank you. I guess we
are out of time, but maybe one question.
Yeah.
Anybody has?
One question. Who's the lucky one?
Who's the lucky one?
No one.
No questions. Okay. Let's thank our speakers.